Hello! So in this video, I'm going to tell you about infinite depth and width limits of deep neural networks. So you might have heard of the infinite width limit. That's like a neural network where it's infinitely wide. But in those limits, the depth of the network is still some finite number. So maybe the network is 10 layers deep, but infinitely wide. In contrast to that, what I'm doing today is infinite depth and width limits. So it's like a network that has infinitely many layers, as well as each layer being infinitely wide. And we'll see that the thing that sort of survives in this limit, the thing that matters a lot, is the ratio of the depth to the width. So even though they're both infinity, by taking a limit, you can make the depth to width ratio anything you want. So this is the ratio d divided by n. And I have for you some simulations to show you how this kind of thing works. And the key thing to highlight is that there's a log Gaussian behavior. So what I have plotted for you here is a histogram. So these plots are a histogram of the log of the output of the network. So you take the output of the network, you take the norm, and you do the log, and that is some number, and then you run that over many simulations, and you plot a histogram of what's going on. The red curve is our prediction from the infinite depth and width limit. The blue curve is what you get if you only do the infinite width limit. And you can see the infinite width limit somehow doesn't know about the depth of the network. It doesn't take into account that as the network gets deeper and deeper, something funny is going on. So here are three different types of networks. Actually, all networks have 100 neurons in each layer, so they're 100 wide. In the first one, it's only one layer deep, so d equals 1. In that situation, the infinite width limit and the infinite depth and width limit are not too far apart, so it's pretty good there. But in this one, the depth to width ratio is 0.1, so this is 10 layers deep. And in this one, it's 100 layers deep, so that's a very deep network. And you can see what's going on is the deeper you get, the more and more spread out things get. So you get more and more variance for deeper networks. That's what the depth and width limit predicts. And I'll say one other thing that I think that is really important to notice is that this is all happening on a log scale. So if you take a look just at this last guy, and you look at, say, between -5 and 0. So that's about one standard deviation for this thing. So most of the time, it'll be between -5 and 0. But about 15% of the time, it's going to be over here. So this is like the top 15% of the network. It's going to be bigger than 0. And 15% of the time, the log of the output is going to be less than -5. And if it's bigger than 0, that's like a e to the 0. Okay, that's like 1. We can deal with that. But being less than -5, that's like an e to the -5. And that's approximately 1 over 150. So what this means is that for these very deep networks, 15% of the time, they output numbers that are 150 times bigger than the other 15% of the time. So you can see that there's a huge amount of variation. So this plot is kind of making things look not so bad because it's all about the log. But if you do the exponential, you see that actually this variance can be really bad for your network. It can say that the network is making things that are much bigger sometimes than other times, and that can be a problem. So this is part of the vanishing and exploding gradient problem and other problems that you see with very deep networks. Okay, so that's a very super duper high level picture of what's going to happen in the rest of this video. And now I'm going to start to get into the math and show you more precisely what's going on. We're going to get more and more exact as we go in. Okay, so let's see what's happening here. So the first thing I'm going to do is define the network. So here's some notation we're going to use. And here is the definition of the neural networks we're talking about today. So this network, it's going to have one layer at the beginning. It's going to have d hidden layers in the middle, and it's going to have one layer at the end. So if we're going to draw a cartoon of the network, we can think of it like this. So it's got an input layer, and we're going to denote the input with an x. It's going to have d hidden layers in the middle here. So there's d of them, d hidden. And it's going to have an output layer. Output. I'm going to call the output z out. And I'm going to call the hidden layers, they're going to be z0 all the way up to zd. So we're applying the hidden layer operation d times. The first layer, that's going from the input to the first hidden layer, this is just a linear layer. So that's why it's just a matrix multiplication, no nonlinearity. So this is linear. The hidden layers are all linear, but by applying this nonlinearity function phi, it becomes a nonlinear function. So here I'm using the ReLU nonlinearity, and that's going to go in the hidden layers. So the usual thing that you do with ReLU nonlinearities. Maybe I'll write that down here. So these are ReLU layers here in the middle. And then in the last layer, I am going to, again, just do something linear. So let's do that in green again. So this is just linear again in the last layer. So that's the setup for the network. The other thing that you should pay attention to that matters quite a bit in these things is the scaling. So I'm initializing all the weights in my network to be mean 0 and variance 1. But in the definition of my network, I'm dividing by the square root of 2 over n in the hidden layers, and I'm dividing by a square root of 1 over n in the last layer, and I'm dividing by 1 over the square root of the input dimension in the first layer. And so by doing that, that makes sure that everything is the right sort of size, so that as we make n and d grow bigger and bigger, that's what we want to do, the infinite width and depth limit. When we do that, everything sort of converges to something nicely. So if you don't do these divisions, then everything's going to explode and things will go bad. These are exactly the right numbers to divide by to make sure that things converge. Okay, that's the definition of the network. Next up is I'm going to tell you I'm going to try to describe how this picture was generated and what happened. And we're going to answer this question, where is the log Gaussian behavior? And so very roughly speaking, what I'm going to tell you about is the following result. And it's about the distribution of the output of the network. So Z out, that's the output of the network. And what are we saying about Z out? We're saying it can be approximated by a product of two things. So one thing is maybe not so surprising. One thing is a Gaussian vector W. So this is a Gaussian vector of size of the output dimension. All the entries are independent mean 0, variance 1 things. So this has mean 0, variance 1, Gaussian entries. So that's not surprising. You might have seen that before. If you initialize the network with Gaussian weights, it's not surprising that maybe it's outputting something slightly Gaussian. And I think a lot of people think of networks as being fundamentally Gaussian. But the important thing to keep your eye on in the infinite depth and width limit is the other factor. And that's this factor over here. So it's e to the 1/2 g. So this is a scalar, and it multiplies the entire network. So unlike the w, whose components are independent, the e to the 1/2 g multiplies every single output of the network. And what this means is that the individual neurons can be extremely highly correlated because of this, the effect of this e to the 1/2 g. So g will be approximately Gaussian, and that, if g is approximately Gaussian, so it's a Gaussian scalar, then e to the g is a log Gaussian vector. So some people call that log normal, but I call it log Gaussian. So this is the log Gaussian from the title, and this is the main result we're going to be talking about, is the output of the network is a log Gaussian scalar times a Gaussian vector. Okay, so that is the main result sort of in a nutshell, and now we're going to get even more precise. So here is a theorem that puts this all together in precise language that makes the limit actually like a precise mathematical statement. Okay, so here's the theorem. Suppose all weights are initialized IID normal 0, 1 random variables. For any depth and width, so no matter what d and n are, the output of the network on initialization is equal in distribution to, and there's a little formula here. Just like before, the formula's got the same three parts as before. So it's got the Gaussian vector W. It's got the funny scalar here, e to the 1/2 g. And there's one other thing that wasn't in there before, a little technicality, that the whole thing gets multiplied by the size of the input. So whatever vector you input into the network, the size of that vector affects the size of the output. It's not surprising if you double the input, you expect the output to double. So this is kind of not a surprising thing. Okay, so this is true for any depth and width. And so any depth d and any width n of the hidden layers. And the point is that the random variable g equals g of nd only depends on the hidden layers. So sort of this, so far, all we've done is we've unpackaged the result of what's going on in the first and last layer. So the first and last layer are these linear layers, and they basically don't matter much. And all of the magic, all of the interesting depth and width stuff is contained in this e to the 1/2 g, and that only depends on the hidden layers of the network. So that is a fact, and that'll be proven as we go on. The interesting part, the super interesting part, is what happens to this random variable g, this scalar that multiplies the whole network. And here's the statement. So in the infinite depth and width limit, the random variable g has the following description. So I'm going to tell you first its mean and its variance. So its mean is minus 1/2 beta. Its variance is beta. Plus there's some little noise. So these are small error corrections. Small corrections that converge to 0 in the infinite depth and width limit. So essentially, its mean is minus 1/2 beta, its variance is beta, and beta is given by this formula. So this is a good formula to keep your eye on. This formula is where the depth to width ratio appears. So it's 5 times d over n. The d over n is the depth to width ratio. And what this is telling you is that the variance of the network is scaling like the depth to width ratio. So bigger depth to width ratio, bigger variance. That's exactly what we saw in the first image up here. So the bigger the depth to width ratio, the more variance you get, and that's affecting the network behavior a lot. Okay, so that is the result of the theorem. I'm gonna make a couple comments about it, and then I'm gonna give a really super simple proof idea of why the theorem is true. And it's really not such a complicated thing. If you keep track of what's going on in the network, it sort of is it just pops out. It's not some super duper magical thing. It's relatively simple in this case. Okay, so a couple things I'll say first. One is the comparison to the infinite width limit. So you might have seen this before in neural networks, doing a limit as the width of the network goes to infinity. And in these things, typically people set the depth to be constant. So they say, I'm thinking of a network with 10 layers, and what I do is I let the width n go to infinity. And if you do that, based on what we found over here, we found that the random variable g, that has a scaling like d over n. And so in this infinite width limit, where depth is constant, if the depth is constant, that's the same as making g go to 0. And if g goes to 0, you sort of lose g entirely. You have e to the 1/2 times 0, that does nothing, and you completely throw away this log Gaussian behavior. So that's why the infinite width limit does not see these funny effects. The infinite width limit makes g equal 0, and in that limit, you don't see the log Gaussian behavior. So this is kind of like throwing away an important part of the behavior. So I will say there's lots of good things about the infinite width limit. So far I've only said bad things about it. So we're throwing out this piece of important behavior. But in the infinite width limit, there's all these simplifications that happen that let you do a lot of cool analysis. So for example, things become asymptotically independent. You can do things like this NTK learning regime, where you can say what training does. So there's all sorts of interesting things you can do in the infinite width limit. And we can't do those things in the infinite depth and width limit yet. So it's interesting open work to see if we can replicate those things in the infinite depth and width limit and do them and still keep track of the contribution from G. So far, the only thing we know how to do is do this kind of situation where we can say what is the distribution at a single point, but we can't go beyond that yet. So that's the infinite width limit, and you can see exactly what it's doing. So this is the same plot as the beginning. So this is the probability density of the output of the network log of z out squared. There's a couple more details here. So one thing I didn't say in the introduction is the input and output dimension of this network are 10. So 10 inputs, 10 outputs. The input dimension really doesn't matter, like you see from this kind of thing. The only thing that matters is the norm of the input. So the fact that it's input 10 really doesn't matter. The fact that it's output 10, that matters a little bit because it tells you the size of this vector w. But really you're seeing, in this plot, you're seeing the effect of the random variable g. So this is very close to the plot of just the distribution of the function g, with a little bit of minor tweaking because of these funny things from the w and the x. But again, so you can see that as the network gets deeper and deeper, you have more and more variance on a log scale, and this is really causing, big fluctuations in the size of the network output. Okay, so that's the comparison to the infinite width limit. Couple little extensions you can do. So one thing that you might be interested in doing, these are fully connected networks, so there's no reason that the hidden layers all have to be the same size. So when I defined the network, I said all the hidden layers, there's d of them, they're all width n, but they don't need to be like that. So you can pick any width you want. So you can have a sequence. So instead of z0 being size n and z1 being size n and all the way up to zd being size n, instead of doing that, you can do any sizes you want. You can do a sequence of sizes n0, n1, all the way up to nd. And if you do that, the same kind of result holds. And in this case, the beta parameter becomes this. It's 5 times the sum of 1 over nl. So instead of doing d over n, it's some kind of like average over 1 over the layer sizes. The other interesting thing you can do is you can ask what happens if I do it with something other than Gaussian weights. So what if I start with independent Bernoulli weights, like 1s and minus 1s in my network? And the same kind of result will hold for any reasonable distribution, so nothing too crazy, like everything needs to have finite mean and variance and that kind of thing. And if you do that, you get the same kind of result. And the proof in that case is much harder, so it's kind of a universality proof. But you can check out this proof if you like in a paper I did with Boris Hannon. So this is exciting work about universality of this depth and width limit. Okay, the other interesting extension you can do that is much more recent is for residual networks. So these are networks where you have skip connections. So we can modify the architecture of our network. When we defined it over here, all I was doing was applying this fully connected ReLU rule. But in real life, people don't tend to use fully connected networks all the time. They tend to have little tricks that sort of make the network better. And one trick is skip connections. So what you do is instead of just purely going from one layer fully connected with weights to the next layer, we also do a convex combination with just whatever was in the previous layer. So it's a convex combination of two terms. The first term is whatever was in the previous layer with a coefficient of alpha. So this is the coefficient. And the other term is going to be exactly what we did before with a coefficient of lambda. And if you do this convex combination, that's called a skip connection, and people think that this improves the trainability of the network. So one thing people say is that this lets the network learn the identity function more easily. And that's because if the network wants to, it can set all the weights to 0, and then you have some kind of identity function coming from this part of the network. So these are called skip connections. And if you do that, the whole thing becomes much more complicated. So these skip connections introduce all sorts of correlations and stuff that make it more difficult to analyze. But the same kind of result holds. And the thing that changes is, the parameter beta that tells you the variance of the Gaussian at the end, that changes. So before it was 5 times d over n, and now it becomes this funny function that depends on the two coefficients, alpha and lambda, that control the feed-forward part of the network and the skip part of the network. So same kind of result for ResNets, for networks with skip connections. And we have a very recent paper with Mufan Li and Daniel Roy on this result. So definitely check that out if you're interested. There's actually quite a few hiccups and funny little things that happen in this situation. So it's a lot more sort of exciting from a math point of view on what happens in this situation. Okay, the last thing I'll say is that you can do the same kind of thing, not just for the output of the network, but also for gradients of the network. So if you do the input-output gradient, that's the gradient with respect to the input of the network, it turns out that that has a very similar behavior to just the output of the network. And the reason this holds is because ReLU networks, they are locally linear. What do I mean by locally linear? I mean on every little piece of space, so for any point in space, there's sort of a little neighborhood around that point on which the function is behaving like a linear function. So z out is equal, for some local neighborhood, some matrix M, which is a random matrix, times the input x. So it behaves like a linear function, but the matrix M changes from place to place in space. But on every little piece of space, it's locally constant. So all of the magic of the nonlinearity in the network is how is the matrix M decided on as you move through space, and this is decided through the activations and so on in the network. But the punchline is that if z out is locally m times x, then the derivative with respect to any input, zxi of z out, is the matrix M times the unit vector ei. And because the network is just z out is m times x, and the derivative is m times ei, that means that the behavior of the derivative is very much like the behavior of z out. You just have to analyze the same random matrix for both, and if you can do that, you can get the result. So So that's why this kind of result holds. And there's a statement of this in this recent paper I told you about on ResNets. And we explore this idea in another paper with Boris Hannon, where we use this to kind of show that the variance of the NTK in this infinite depth and width limit is large. So we show that there's at least this like d over n variance for things like gradients of the network. Okay, I think that was everything I wanted to say. I explained this picture. Let's see, am I forgetting anything? Okay, so now I'm going to go ahead and jump to these sketches of the proof. I'm going to give a very simple sketch. So the simple sketch, this is like the, I guess it's the math version of explain like I'm 5. So it's like maybe explain like I'm a 5th year student or something. And then I have a detailed version of the proof that really does like all the actual proof down here. I'm not going to explain the detailed version in the video. So if you want to see that, you have to download the notes, which should be in the description. But here's the explain like I'm 5 version of the proof. So the first thing to prove is this thing about the equality and distribution. So is this thing. And this is only happening because of the effect of the first and last layer. So let's explain why this happens. Okay, so the key property that we're going to use, the key property of Gaussian random matrices. So if you have a matrix where all of the entries are independent Gaussians, the thing about that is when you multiply by any vector, what you get in distribution is a Gaussian vector. So a Gaussian matrix times any vector, no matter what it is a Gaussian vector. And that's just because you're doing linear combinations of Gaussians, you get a Gaussian. So the only possible potential thing that could screw you up is how you scale everything. And it turns out you scale by the norm of the thing you input. And so if you know about that anytime you multiply by a Gaussian matrix, you get a Gaussian vector. And you look back to the definition of our network. So here is the definition of our network. In the first layer, we're multiplying by a Gaussian matrix. In the last layer, we're multiplying by a Gaussian matrix. So the hidden layers have this funny nonlinearity that makes things more complicated. But in the first and last layer, it's purely just this linear Gaussian multiplication. And so what that means is that after the first and last layer, you're working with Gaussian vectors. So z0, no matter what x is equal to some Gaussian vector times a scalar that depends on the size of the input. Similarly, z out, so z out, that's the output of the network. It's a Gaussian vector times a scalar, and the scalar depends on zd. So this is exactly what we said earlier, is that the output of the network is a Gaussian vector times a scalar. And we just have to package up the scalar to make the capital G that we talked about. So if you define capital G like this, then we get exactly the result we had before. So if G is defined like this, then this result here is saying precisely that Z out equals e to the 1/2 G times this Gaussian vector. And because of this factor over here, this also comes in to give a norm of x divided by square root of n. So the first fact is really just because of the first and last layer of the network, which are linear layers. Okay, so now we got to work on what is the distribution of G. That's where all the magic happens, proving that G is a Gaussian vector, or sorry, a Gaussian scalar. So proving that G converges to a Gaussian scalar. So how are we going to prove that it converges to a Gaussian? We're going to use the central limit theorem. That's how we prove everything converges to a Gaussian. We use the central limit theorem. So let's see how that goes. So the first step we do is we look back to our definition of the layers. So remember, to get from one layer to the next layer, we did this. We said ZL plus 1 is equal to square root 2 over n times phi of ZL. And what we're going to do is we're going to divide both sides of the equation by the norm of ZL. So we're going to divide this by the norm of ZL. Okay, I forgot to multiply by the Gaussian matrix that's going on here. So let me put that back in. So it's a Gaussian matrix, WL, the weights in layer L, times the output of the previous layer. And I divide by the norm of ZL. And now I'm going to use a funny property of the ReLU function, which is that the ReLU function is homogeneous. So if you do phi of a constant times x, you can pull the constant in and out of the ReLU function. So there is the homogeneity. This is called homogeneity of the ReLU function. So you can pull constants in and out. And over here, I am dividing by the norm of ZL. And what I'm going to do is I'm going to just suck that right up into the ZL to get the unit vector. So this is what I'm calling Z hat L. is ZL divided by the norm of ZL. And so by using homogeneity, we can turn this ratio of what's going on from layer L plus 1 to what's going on in layer L, that turns into something involving this unit vector. Okay, and now I'm going to do the trick one more time about Gaussian matrices. So when you multiply by a Gaussian matrix, you get a Gaussian vector. And so if you do that trick one more time, you get this Gaussian vector GL plus 1, which is a Gaussian vector, and we're multiplying by a scalar, which depends on this unit vector. So we've turned the problem of understanding the random variable g, which is a log of something, into where we're analyzing these ratios of how things change from one layer to the next layer. And they involve the norm of these unit vectors. Okay, now we're going to take the norm of both sides. And when you take the norm of both sides, you get this equation. So ZL plus 1, the ratio of the norms, ZL plus 1 to ZL, is a multiple of two different things. There is a norm of this unit vector involving the ReLU, and there is a norm of a Gaussian vector. And if you combine these two things, you can get a telescoping product for the norm of ZD. So the norm of ZD is the product of this ratio over all the layers. So that's what we're doing here. And because each thing is a product of two things, we get a big product over here, and it's a product of, there's two terms in each term of the product, and there's D layers, there's D terms. There's also one term right at the beginning, and that's coming from Z0. And the key fact that I used, that I'm using now, is that if ZD is a product of D things, then we take the log, we get a sum of D things. And this is why the central limit theorem is going to work. So ZD is a big product, and there's a way to simplify it, so I'm going to skip the details on how exactly you simplify it. You simplify it. But by combining things, you can turn it into a product of D things. So here it was a product of 2D things. Product of 2D things. And here I've simplified it. It's a product only of D things. And the trick again is to use the homogeneity of the ReLU function to combine some of the terms. And if you do that, you get this product of D things. And now G is the log of this. So what's left over? G is the log of this thing. The log of a product of D terms is the sum of D terms. So G becomes the sum of D terms. Okay, and I lied when I said there's D terms. There's a big product with D things, but there's also this one little guy floating off at the end. And that's what's going to happen in the sum too. We have a sum of D terms plus one extra term. So there's the last term. And in fact, what's going to happen now is each of these terms are going to give a tiny contribution to the final value. So we're summing over D things, that's the depth of the network, and the infinite depth and width limit, that is a huge number of things, right? We're summing up more and more things. But each individual term is going to have a contribution only on the scale 1 over n. So by adding up D things that are each 1 over n, that's how we get the D over n in the actual statement of the theorem at the end. Okay, so the approximation that is going to happen is that each of these things is approximately Gaussian. Why is that true? It's because we're looking at the norm of n-dimensional vectors. And the norm is kind of a sum over the components. And because these are Gaussian things, the components are independent. So each individual term is a Gaussian vector whose variance is like 1 over n. So the variance of this term is precisely 2 over n. And the variance of coming from this term up here, is going to be 5 over n. And there's sort of a simple calculation you can do to figure out these 2 over n and 5 over n. And the details, again, are in these notes if you want to see them carefully. But for now, just believe me that they're 2 over n and 5 over n. So these terms over here, there's d of them. They each have a variance of 5 over n. These terms, this term rather, there's only one of it, and it has a variance of 2 over n. And so if you take the log and you keep track of what's going on, you'll see that at the end of the day, what you get is a sum of Gaussians. There's d of them that have a variance 5 over n, plus one extra term, which is a Gaussian, of variance 2 over n. And if you put those together, that is where this beta parameter 2 over n plus 5 d over n comes from. So there's, in the d layers, you get a 5. In the last layer, you get a 2. And each term has variance 1 over n, which is why the contributions are small, but add up over d layers. So that's very roughly speaking the idea. You have to use the fact that there's some logs going on. That explains why the mean is shifting down a little bit. So you can check out the details if you want in these notes. I've tried to make them extremely readable, and I think that even the detailed proof is not super hard. So anybody who's taken like a an advanced probability course, I think should be able to understand this. It's all about just computing these things and computing things like these approximations that I talked about and making sure that everything lines up. Okay, so I hope you enjoyed that. I hope you got something out of it. And I hope you remember that the deeper you make your network, sort of the more badly behaved it is in terms of log Gaussian behavior.